So thank you very much. Thank you. So I'm going to present you the first demonstrator linked to CExA project, which is Gysela-X++ demonstrator. His goal is to go to exascale plasma turbulence simulation. And this is a joint work with the Gisela team, CExA team, and also Emily Bourne from CETAS, EPFL, and ITP Virginie with a PhD thesis of Alex Hoffman on polling. Sorry, you see my slide moving?
Perfect.
Okay. So just some context, the Gisela code, for the Gisela code, the gyrokinetic plasma turbulence simulation are necessary to understand turbulent transport that mainly governs confinement in tokamaks. And Gisela code is developed at CEA ITER over 20 years. Strong collaboration between physicists, mathematicians, and HPC specialists in Europe. This is a Fortran90 code parallelized with MPI plus OpenMP and optimized up to more than 700,000 CPU cores. It has, for instance, a relative efficiency of 85% on more than 500 cores and 63% on 730,000 cores. And this test were done on CExA machine 2 or 3 years ago. In terms of HPC resource, it has an intensive use of petascale resources because we consume around 150 million hours per year via GMC, HPC, and HPC fusion resources. And we know that we will need exascale simulation for ITER plasma turbulence simulation. So what is the roadmap for Gisela towards this exascale simulation? First point is that we have decided to pre-develop a new code that will be called Gysela-X++. And why we decide that? The first point is in terms of HPC. We found with the Gisela Fortran code and with the first test we have done to try to port the code on a new accelerated architecture, that it was very difficult to keep one unique code to have performance on this different architecture. And so the challenge for the new code is to have a portable code on this new exascale architecture. And for that, we decided to develop this code in modern C++ with MPI plus Kokkos. And this is not only a simple translation of the existing code, because we want to take the opportunity of this rewriting to add more physics, and this will also add new numerical challenges. First one is that we want to, in terms of physics, to have more realistic density and temperature gradients at the edge of the plasma. And so for that, we had to develop a semi-Lagrangian scheme for non-uniform meshes. And this was part of the PhD of Emily Bourne a few years ago. We had a first proof of concept in this thesis. The second point is that we want to have X-point geometry to be have a more realistic geometry for the current tokamak and also for ITER. And this, in terms of numerics, that means that we have to develop semi-Lagrangian schemes for multi-patches. And this is the subject of Pauline Vidal PhD at IPP Garching. And we also needed to develop 2D multi-patches Poisson solver. And this is part of the PhD of Alex Hoffman, also at IPP Garching. And finally, more recently, we decided also to be able to look at the stellerator configuration. And for that, we need a 3D scalable Poisson solver, and this will be part of the PhD of Gysela-X at CERFAS. In terms of roadmap for Gysela-X++, the first objective is to have an efficient parallel code to exploit Alice Lecoq resources at the arrival of the machine at TGCC in 2026. And this project is funded by several funding. The first one was the PTC simulation dose. So not the main shot that we discussed today, but there is also the rewriting of the code is also part of the Kokkos 3 European Center of Excellence. And for all the parts concerning the IO plus in situ diagnostic development in AI, we have also funding from ITER and INPEX EXADOS. And finally, we also succeeded in having funding via BPI in the Renaissance startup to develop the stellerator version of Gysela. And the idea of this rewriting was to base the code on an external library. So we have to keep in mind that it's completely different philosophy that we had before for the Fortran code, where we didn't have a lot of dependency to libraries. The first one for this new version is to base the domain discretization on DDC that you already heard this morning, and to use Kokkos. So Kokkos, at least for FFT and spline, but also for linear algebra, we already tested Ginkgo or Egan, and we are also based on the deep Colliot, a new library that has been developed by Etienne Malabeuf at CNES for collision operator. I'm going to come back on this later. And finally, for the CIO, we decided to base, as it was done in the Fortran code, the IO on the PDI data interface. So the advantage of this all this external library is that we can have the optimization of each library on an accelerated architecture, on that we can take advantage of that. The con of this multiple external library dependency is that it's more complex to install, so that we need robust packaging tools for that. So let's start with the first thing that we have developed since two years, which is the Gysela-X library, which is a collection of C++ components for writing gyrokinetic semi-Lagrangian codes. And where we are now, we have all computing kernel ready for non-uniform mesh, and there is a work in progress for multi-patches version of it. So in terms of computing kernel, we have Vlasov solver with advection operators, collision operator also, and such terms. And we also have the different Poisson solver. So all the ingredients that we need to write some Lagrangian code. And we start to use this different operator to construct several Vlasov Poisson simulation. So we have no 1x, 1v Landau damping, also 1x, 1v down-pointed instability. And finally, we also have 2x plus 2v Landau damping possibility. And you see here that all this work is available on GitHub. We have now a packaging via Spark and try to develop with model simulation via PPR Numpex Gwix packaging. We also have the oxygen documentation and a large number of unitary and non-regression tests, because we have more than 400 tests via CI integration. Let's start with the first prototype, which is a 2D monogeometry prototype called VoiceXX code that is based on this Gysela-X library. This is a code 1x and 1v that has been developed for SHIS simulation. So if you want some details for numerics, you can look at InVivo paper, and if you want more to know about what is possible to do with this code in terms of physics, you can look at Jan Munchi paper. So this was the first CExA demonstrator, fully based on Kokkos and portable on multi-architecture. So here you see the first results that we have with this prototype. The first figure is a time versus the number of point comparison between GPU architecture for V100 NVIDIA and in blue and AMD MI 250 in red, and compare to CPU architecture, but so this is a serial version because we try OpenMP version, but we still have an error on Genoa architecture, so some things that we have to fix. But you see that we are already able to run on the different architecture without changing anything except the compiling in the code. And these are the results for the different operators in the code for Android and Adastra GPU GPUs. So I won't go into all the details, but and this is still work in progress to try to improve the code. But we already see that there is a factor more than 3.5 between AMD MI 250 compared to V100. I think it's part of what is expected for this version. And so this code is ready for physics, and even if it's a 2D code, we plan already to do a lot of work with this code at IOFM, with starting of a new PhD with Mathieu Perret, who is going to use this code for neutral injection simulation. Plus, we have in mind to use this code for PIN studies with NTU at Singapore. In terms of work in progress, what we have, what we are doing now is to develop a 4D multi-GPU prototype, which is called Gysela-X. that is 2X and 2V semi-Lagrangian code for axis-symmetric neoclassical simulation. So all the pieces of the puzzle are being put together. That means we have all operators already ready in the Gysela-X, meaning 2D advection in R theta plus 1D advection in the V parallel direction. So this all these advections are based on non-uniform 1D and 2D spline that you already heard before with Thomas. And this is a very good example of the joint work that we have had with DDC because it was developed in DDC via the PTC simulation with Baptiste Legui, and it has been after optimized with Kokkos tools via the moonshot CExA. So I think it's a very good example of all the chain to obtain at the end something that is ready for us, but also for all the community. And so we have also 2D Poisson solver already ready, and 2D collision operator. So for the collision operator, this one was fully translated from the Gisela 490 version into C++, sorry, and Kokkos. This has been done by Etienne Malabert. And there is now independent library called libcolliope, who has also an interface both for the Gisela 490 code and the new code. So that means that this optimization will also benefit to the platform code. And finally, we have started to work on the MPI transposization because, as I said, one of the differences with this new prototype is the fact that we will have to work on multi-GPU. The objective for this prototype is to be ready for the end of this year, and this is one of the milestones of the ECO3 project. So, as I said, this prototype is designed to work on multi-GPU, and it will help to learn how to optimize the code for multi-GPU. But it will be also used by physicists to study a neoclassical effect with the shaping on impactive. This is part of the PhD of Ludovica at CEA, and we will also have work with Entius and Batova on this part. So, in terms of conclusion and perspective, we start a full-base Kokkos ecosystem that is under development for gyrokinetic turbulence simulation. And clearly, the long-term collaboration we have with the Maison de la Simulation plus this CExA shot has clearly been a booster for this development. And you have to keep in mind that the main goal and objective we have for the next years is to be able to have exascale electromagnetic simulation for ITER plasma and also for stellerators. So in terms of architecture, so the Gysela-X is a library where all the maths components are put and will be put in the future. This library is based on DDC for all the domain discretization, plus libcolliope for the collision operator, and finally we use PZI for IO. So where we are now, we are already succeeding constructing a first 2D prototype, which is called Gysela-X, and that will be used for sheet simulation. We are now working on a 4D prototype Gysela-X that will be ready for the end of this year, and that will be used by physicists for neoclassical effects study. The next plan are to develop another 4D version, but this version will be 3D in space plus 1D in velocity. And this will be the starting point for a test bed for aligned coordinates numerical scheme development that we will need to improve the adding of the full kinetic electrons, but also for the next future for stellerator. And finally, the step that we have in mind for the arrival of Alice Kokkos is the Gysela-X++ code, which will be as the Gysela-14 code 5D code, 3D in space plus 2D in velocity. And what we have in mind for that is to be able to run exascale simulation with X point. And for so this plan for 2026, I would say, and for the 2028, we have in mind to have also a stellerator version of Gysela, which we needed more complex geometry in 3D that we have for the Kokkos version. So all this work is not possible without a strong collaboration between HPC specialists, mathematicians, and also physicists. So what we wanted was to have for each prototype the possibility to be exploited by the physicists, because the idea was to that the physicist takes the habit to use this C++ version in parallel of the using of the Fortran version in the 2 or 3 next year. And so, as I've already said, we have worked a lot with the CExA team, and we still have a future work for CExA. This is a non-exhaustive list, but what we already have in mind is we need optimized 6D transposition. 6D because we have to deal with 3D in space, 2D in velocity, but also different spaces, because we have ion, electron, but we want also to have imperative. So for the moment, it is a bottleneck with Kokkos because there is a limitation to 5D. We want also optimize spline in 3D and also in 4D. And what we need for sure is for the future is training for new developers, but also for users. I think we also still need an improvement of the readability of the code, because it's not so simple for physicists and for all to go from Fortran 90 to this modern C++ with a lot of template plus Kokkos. And we will also need a continuous integration helper to have all our tests on new integration tests working on multi-architecture. And finally, there are missing numerical kernel that we need for Gysela-X++ with X point. For instance, we will need a gyro average operator that will be extracted from Gysela Fortran 90 as it has been done for the collision operator. But we will also need a Vlasov solver on multi-patches, and there are a lot of numerical issues for this that are in progress at IPP. And finally, I take the opportunity to thank all people working on this project, and I have a special thanks to Emily Bourne, Thomas Padolo, and Julien Bigot, who has done all the work concerning the architecture strategy for this new framework. And I've developed a lot for Gysela-X. I want also to tell many thanks to the CExA team, and just to remind you that all this work is funded by Moonshot CExA, but also was funded by PTC simulation those, and also Kokkos products. If you have questions, thank you for your attention.
Thank you very much, Virginie. So we have time for just maybe one very quick question while we switch presentation. Are there any questions? Edouard, you have your microphone open. Do you have a question?
Can you hear me?
Yes.
Oh, sorry, I muted you. I thought it was a mistake.
Is it okay? No, Virginie, I would like to know if you have a feedback from a scientist who were more, I would say, Fortran user about the new code, and I mean, are they comfortable with it? Can they use the similarity between Kokkos view and Fortran array to get a bit into the code, and how? Because I think it's this transition can be important for many people.
Yeah, I'm not sure that I can answer now, because we are really at the beginning of the using of the code by physicists. So this one is ready since 2 months, I would say, and the PhD student will start next month. But Peter Donnell, who is one of the physicists of the Gysela-X team, has been involved in all the strategy of development of this framework, and he already started to use the code for developing the validation test for the collision operator, and it seems that it's not too complicated for him, but as I have said, we still have, I think, to improve the visibility of the code to make it simpler for physicist user. But what we had in mind is to involve the physicists as soon as possible, like that they can take the habit of this new architecture, and we will have their feedback to try to improve the code. But yes, it's we will start. I will have more answer for your question in 2 or 3 months. At the beginning of next year, we will already have more feedback on this. But sure, it's a difficulty of this modern C++ framework. Yeah. And we have to change our habits.
Thank you, Virginie. Okay, given the time constraints, I think we will switch to the next presentation.